Hello, science fans. Let's talk about the amazing world of computer programming. Imagine you're building something with Lego bricks. You don't just have a pile of plastic, you have specific pieces. You have a red 2x4 brick, a blue window piece, and a little person with a hat. Each of these pieces has properties, like its color and size, and things it can do, like connect to other bricks. In the world of Java programming, we have something very similar called an object. An object is a self-contained unit that bundles together data, its properties, and the actions it can perform, which are its methods. It's a fundamental concept that helps us model the real world inside our computers, making our code more organized and easier to understand. Think about a real-world object like a car. A car has properties, right? It has a color like red, a model, maybe a convertible, and a current speed, say 60 miles per hour. These are its data. A car can also do things. It can start its engine, accelerate, and brake. These are its actions, or what programmers call methods. In Java, we create a blueprint for a car called a class. This class defines all the possible properties and actions a car can have. Then, from that single blueprint, we can create many individual car objects, each with its own specific properties. One car object could be a blue sedan, and another could be a yellow sports car, but they both came from the same car blueprint. So how does this look in code? It's simpler than you might think. We first define the class, which is our blueprint. It might look something like this. Class car, string color, void start engine. Here, we've said that any car will have a color and a way to start its engine. To create an actual tangible car object that we can use, we write a line like this: car my car = new car. This command tells the computer to take our car blueprint and build a brand new car object in its memory. We can then interact with it, maybe setting its color with mycar.color = green, or telling it to get going with mycar.startEngine. This approach is incredibly powerful. Instead of writing messy, tangled code where data and actions are all mixed up, we organize everything into neat, reusable objects. We can create a dog object with a bark method, a bicycle object with a pedal method, and a bank account object with deposit and withdraw methods. Each object manages its own state and behavior, just like things in the real world. This makes our software more reliable, easier to debug, and much simpler to expand upon later. It's the science of building complex digital systems from simple, understandable parts. Consider it. Now that we know what an object is, let's explore the 4 fundamental principles that make object-oriented programming, or OOP, so effective. These are often called the 4 pillars, and they provide the support structure for writing clean, efficient, and scalable code. Think of them as the rules of the road for our object-driven world. The first pillar is abstraction. Abstraction means hiding the complex, messy details and showing only the essential features. When you drive a car, you use a steering wheel, pedals, and a gear stick. You don't need to know about the combustion in the engine cylinders or the intricate workings of the transmission. The car's interface is simplified for you. In programming, abstraction lets us create objects with simple interfaces, hiding the complicated logic inside. The second pillar is encapsulation. This is a big word for a simple idea, bundling data and the methods that operate on that data together in one unit or capsule. It's like a pill capsule that holds the medicine inside, protecting it from the outside world. In our car object, the car's speed and the accelerate method are bundled together. Encapsulation also means protecting the data from outside interference. We can make the speed variable private, so other parts of the program can't just change it to a random number. They have to use the accelerate or brake methods, which ensures the speed changes in a controlled, realistic way. It's all about data safety and control. The third pillar is inheritance. This is all about creating new classes based on existing ones. It's a way to reuse code and establish a relationship between objects. Think of a family tree. You inherit traits from your parents like eye color or height. In OOP, we can create a general vehicle class with properties like speed and methods like move. Then, we can create more specific classes like car, bicycle, and boat that inherit from vehicle. These child classes automatically get all the properties and methods of the parent vehicle class, but they can also add their own unique features. A car might add a honk horn method, and a boat might add a drop anchor method. It's a powerful way to avoid repeating code. Finally, we have the fourth pillar, polymorphism. This sounds complicated, but it just means many forms. It allows us to use a single interface to represent different types of underlying objects. Let's go back to our vehicle example. we could have a list of different vehicles: a car, a boat, and a bicycle. Even though they are different types of objects, they all inherited the move method from the vehicle class. Polymorphism lets us call the move method on each one, and each object will respond in its own appropriate way. The car will roll its wheels, the boat will propel through water, and the bicycle will turn its pedals. We use the same action, move, but we get different results depending on the object. It makes our code more flexible and dynamic. We've talked about inheritance, where a new class can get its features from a parent class. It's like a child inheriting traits from a parent. But what if a child could inherit from two parents at once? In some programming languages, this is possible, and it's called multiple inheritance. However, Java was designed to be simple and safe, and it deliberately does not allow a class to inherit from more than one other class. Why? Imagine two parents, a musician class with a perform method, and an athlete class that also has a perform method. The musician performs on stage, while the athlete performs on the field. If a new student class tried to inherit from both, which perform method should it use? This conflict is known as the diamond problem, and it can create ambiguity and bugs that are hard to track down. To avoid this confusion, Java's designers made a choice. A class can only have one direct parent. This keeps the family tree simple and predictable. But what if we still want our student class to have the abilities of both a musician and an athlete? This is where interfaces come to the rescue. Think of an interface not as a parent, but as a contract or a certification. An interface is a collection of method names without any of the code inside. It just says, any class that implements me must promise to provide its own version of these specific actions. It's like getting a pilot's license. The license guarantees you know how to take off and land, but how you do it depends on whether you're flying a jumbo jet or a small propeller plane. So, we could create an interface called playable with a perform method, and another interface called trainable with a train method. Our student class can't inherit from two parent classes, but it can implement as many interfaces as it wants. It can promise to fulfill multiple contracts. The student class would declare that it implements both playable and trainable. This means it must provide the actual code for the perform method. Maybe the student plays the guitar and the train method. Maybe the student runs track. This gives us the flexibility of multiple inheritance without the messy ambiguity. A class has one true parent, inheritance, but can wear many hats, interfaces. To summarize the difference, an abstract class is like a partial blueprint. It can have some methods with code already written and some abstract methods that must be completed by its children. A class can only extend one abstract class. It's for when you want to provide a common base with some shared functionality. An interface, on the other hand, is a pure contract. It typically only contains method signatures, the what, not the how, and constants. A class can implement many interfaces. It's for when you want to define a capability or a role that different unrelated classes can share, like being clickable or serializable. So, you use inheritance for is-a relationships, like a car is a vehicle, and interfaces for has-a capability relationships, like a button has a clickable capability. Beyond the 4 pillars of OOP, there's another set of guidelines that expert programmers follow to build software that is understandable, flexible, and easy to maintain. These are known as the SOLID principles. It's an acronym where each letter stands for a different design principle. Think of them as the pro tips for organizing your code. They help you avoid creating a tangled mess and instead build systems that can grow and change over time without breaking. Sticking to these principles makes you a better collaborator and a more effective problem solver. Let's take a quick look at what each letter means, using simple everyday examples to make sense of it all. The S in SOLID stands for the single responsibility principle. This one is straightforward. A class should have only one reason to change. This means it should have only one job or responsibility. Imagine a Swiss Army knife. It's cool, but if the corkscrew part breaks, you might have to replace the whole thing. A better design is a drawer of kitchen utensils. You have a knife for cutting, a spoon for stirring, and a can opener for opening cans. Each tool has one job. In code, you shouldn't have one giant class that connects to the database, handles user input, and calculates business logic. You should have separate classes for each of those jobs. The O stands for the open-closed principle. This principle states that your software entities, like classes or modules, should be open for extension but closed for modification. What does that mean? Think of it like a smartphone. You can add new functionality by installing new apps. It's open for extension. but you don't have to open up the phone and rewire its internal circuits to do so. It's closed for modification. In programming, this means you should be able to add new features to your system without changing the existing tested code. This is often achieved using inheritance and interfaces, allowing you to plug in new behaviors without disrupting the old ones. Next up is L, the Liskov substitution principle. This is a fancy way of saying that objects of a child class should be able to replace objects of the parent class without breaking the application. If you have a bird class with a fly method, and you create a penguin class that inherits from bird, you have a problem. A penguin is a bird, but it can't fly. If your program expects any bird object to be able to fly, substituting a penguin object will cause an error. This principle guides us to create inheritance hierarchies that make sense. A better design might be a bird class, with flying bird and non-flying bird as child classes. The I stands for the interface segregation principle. This means that clients should not be forced to depend on interfaces they do not use. Instead of one big, general-purpose interface, it's better to have several smaller, more specific ones. Imagine a restaurant with one giant menu that includes breakfast, lunch, dinner, and drinks. If you're just there for a coffee, you still have to sift through pages of steak and pasta options. It would be better to have separate menus. In code, if you have a fat interface with 20 methods and a class only needs to implement 2 of them, you are forcing it to carry extra baggage. It's better to break that interface into smaller, more focused ones. Finally, the D is for the dependency inversion principle. This principle states that high-level modules should not depend on low-level modules. Both should depend on abstractions. And abstractions should not depend on details. Details should depend on abstractions. Whoa, that's a mouthful. Let's simplify. Think of a TV remote. You, the high-level module, don't need to know the specific electronic details of your Samsung or Sony TV, the low-level modules. You just interact with a standard set of buttons, the abstraction. The remote works with any TV that follows the standard button interface. In code, this means your main business logic shouldn't depend directly on a specific database or a specific payment gateway. It should depend on an interface, allowing you to swap out the specific implementations later without rewriting everything. In a perfect world, our programs would run flawlessly every single time. But we live in the real world, where things can go wrong. A user might enter text where a number is expected, a file we're trying to read might not exist, or a network connection could suddenly drop. These unexpected events are called exceptions. An exception is an error that disrupts the normal flow of a program's instructions. When an exception occurs, the program stops what it's doing and looks for a way to handle the problem. If it can't find a way to handle it, the program will crash. Think of it like a safety valve in a pressure cooker. When the pressure gets too high, the valve releases steam to prevent an explosion. Java has a powerful mechanism for dealing with these errors gracefully, called exception handling. Instead of letting the program crash, we can anticipate potential problems and provide a backup plan. We do this using a try-catch block. We place the code that might cause an error inside the try block. It's like saying, let's try to do this risky thing. Immediately following the try block, we add a catch block. The catch block contains the code that will run only if an exception occurs in the try block. It's our plan B. For example, try int result equals sign 10, 0, catch, arithmetic exception E, system out.println, oops, you can't divide by 0. This code attempts a division by 0, which is impossible. Instead of crashing, the program jumps to the catch block and prints a friendly message. In Java, exceptions come in 2 main flavors, checked exceptions and unchecked exceptions. The difference is all about when the compiler checks for them. Checked exceptions are problems that a well-written program should anticipate and recover from. Examples include trying to open a file that isn't there, like file not found exception, or a network issue, like I/O exception. The Java compiler checks to make sure you have handled these possibilities. If you write code that could cause a checked exception, your code will not even compile unless you use a try-catch block, or declare that your method might throw the exception. The compiler forces you to have a plan. Unchecked exceptions, on the other hand, are problems that usually result from programming errors or other unrecoverable situations. These include things like trying to access an object that doesn't exist, such as null pointer exception, or trying to access an array element with an invalid index, like array index out of bounds exception. The compiler does not force you to handle these. The reasoning is that these errors reflect bugs in your code that should be fixed, rather than handled gracefully. You shouldn't try to catch a null pointer exception. You should fix your code so that the pointer is never null in the first place. So think of checked exceptions as external, environmental problems you must plan for. and unchecked exceptions as internal logical mistakes you should fix. Section 6. Organizing your digital stuff, the collection framework. Imagine you have a huge collection of comic books. How would you organize them? You could stack them in a pile, line them up on a shelf in the order you bought them, put them in a box where duplicates are not allowed, or create an index card system that links each character to the comics they appear in. In Java, when we have a group of objects, we need similar ways to organize them. This is where the Java collection framework comes in. It's a unified architecture for representing and manipulating collections of objects. It provides a set of pre-built data structures and algorithms, so, you don't have to reinvent the wheel every time you need to manage a group of items. The framework is built around a few core interfaces. The three most important ones for beginners are list, set, and map. A list is an ordered collection, like your comic books lined up on a shelf. The order is preserved, and you can have duplicate items. You can have 2 copies of the same issue right next to each other. This is perfect for when the sequence of items matters, like the steps in a recipe or a list of high scores from a game. The most common implementation of a list is the array list, which is great for most general-purpose list needs. A set, on the other hand, is a collection that does not allow duplicate elements. It's like your box of comics where you only keep 1 copy of each unique issue. If you try to add an issue that's already in the box, it simply won't be added. The order of elements in a set is not guaranteed, though some implementations do maintain order. A set is ideal when you only care about the presence of an item, not how many times it appears or in what order. For example, you could use a set to store a list of all the unique students attending a school or the unique words in a document. Finally, we have the map. A map is a bit different because it doesn't just store individual items, it stores key value pairs. Think of it like a dictionary or your index card system. The key is the word you look up, like Superman, and the value is the definition or the list of comics he's in. Each key in a map must be unique. Map is incredibly useful when you want to retrieve a value based on a specific identifier. You could use it to map student ID numbers to student objects, or usernames to user profiles. It provides a very fast way to look up information if you know the key. Together, list, set, and map provide the fundamental tools for organizing almost any group of objects you can imagine. Section 7. Doing many things at once. A look at threads. Have you ever tried to pat your head and rub your stomach at the same time? It's tricky, but your brain is essentially trying to manage 2 separate tasks at once. Modern computers do this all the time on a much grander scale. You can listen to music, browse the web, and download a file simultaneously. This is made possible by threads. A thread is the smallest unit of execution within a process. You can think of a program as a large task, and threads are the individual workers assigned to carry out smaller parts of that task concurrently. A simple program might have only one thread, the main thread, which executes instructions one after another. But a complex application can use multiple threads to perform multiple operations at the same time. Using multiple threads, a concept known as multi-threading, can dramatically improve the performance and responsiveness of an application. For example, in a word processor, one thread could be responsible for responding to your keystrokes and displaying text on the screen, while another thread in the background is busy checking your spelling and grammar. This way, the user interface remains smooth and responsive, even when the program is performing a heavy, time-consuming task in the background. Without threads, the entire application would freeze until the spell check was complete, which would be a very frustrating user experience. A thread in Java goes through various stages in its life, known as the thread lifecycle. First, it is in the new state. This is when the thread object has been created, but the start method hasn't been called yet. It's like a worker who has been hired, but hasn't started their shift. Once the start method is called, the thread moves to the runnable state. It's now ready to run, and is waiting for the operating system's scheduler to give it some CPU time. It's not necessarily running yet, but it's in the queue, ready to go. A thread can move from runnable to a blocked, waiting, or timed waiting state if it's waiting for a resource, like a file, waiting for another thread to finish, or has been put to sleep for a specific amount of time. Once the condition it was waiting for is met, the thread moves back to the runnable state, ready to be picked up by the scheduler again. This cycle of running and waiting can happen many times. Finally, when a thread has finished its job and its run method is complete, it enters the terminated state. The thread is now dead and cannot be started again. It's like the worker's shift has ended and they've gone home for the day. Understanding this life cycle is key to managing threads effectively and writing robust, concurrent applications that can juggle multiple tasks efficiently without getting into a tangled mess. Section 8. Java's Evolution. Cool new tools in Java, 8 and 11. Java has been around for a long time, and just like any good science, it's constantly evolving. Two of the most significant updates for modern Java development were Java 8, released in 2014, and Java 11, released in 2018. These versions introduced new features that made writing code simpler, more concise, and more powerful, especially for beginners. Java 8 in particular was a revolutionary release that changed how programmers write Java code. One of its biggest additions was lambda expressions. Before lambdas, if you wanted to pass a small piece of behavior to a method, you had to create a whole new class. It was cumbersome. Lambda expressions let you treat functionality as a method argument. It's like giving someone a quick one-line instruction instead of a full formal manual. For example, if you wanted to sort a list of strings by their length, you can now do it in a single, readable line of code using a lambda expression. This concise syntax reduces boilerplate code and makes your intentions clearer. Another massive feature in Java 8 was the Stream API. Streams provide a new way to process collections of objects. Instead of writing loops to iterate over a list and perform operations, you can chain together a sequence of operations in a declarative way. You can filter, map, sort, and collect data from a list with a fluent, easy-to-read syntax. We'll explore this more later, but it fundamentally changed how developers work with data in Java. Java 8 also introduced the optional class, a container object which may or may not contain a non-null value. Before optional, a common source of bugs was the dreaded null pointer exception. A method might return null to indicate no result was found, and if the programmer forgot to check for null, the program would crash. Optional provides a clear, explicit way to handle cases where a value might be absent. It forces the programmer to think about the empty case and handle it properly, leading to more robust and reliable code. It's like a box that clearly says contents may be empty. Check before opening, instead of just handing you an empty box and hoping for the best. Then came Java 11, which was the first long-term support release after Java 8. While not as revolutionary as Java 8, it brought some nice quality-of-life improvements for beginners. One of the most convenient features is the new ability to launch single-file source code programs directly. Before, you had to first compile your Java file with javamyprogram.java, and then run it with Java myprogram. With Java 11, you can just type javamyprogram.java, and it will compile and run it in one step. This is fantastic for learning and for writing small utility scripts. Java 11 also added some useful new methods to the string class, like isBlank, lines, and strip, which make common string manipulations much more convenient. Section 9. Advanced Blueprints, Design Patterns, Hibernate, and Spring. As you move from writing small programs to building large, complex applications, you'll find that you encounter the same kinds of problems over and over again. Design patterns are general, reusable solutions to these commonly occurring problems within a given context. They are not finished code, but rather blueprints or templates that you can customize to solve a particular design problem in your code. They represent the collective wisdom of experienced software developers. A few common patterns are especially helpful for beginners to know. The singleton pattern ensures that a class has only one instance and provides a global point of access to it. This is useful for things like a database connection or a configuration manager, where you only ever want one object managing that resource. The factory pattern provides a way to create objects without specifying the exact class of the object that will be created. Imagine a pizza place. You tell the cashier you want a vegetarian pizza, the factory, and they handle the process of creating the specific mushroom pizza or spinach pizza object for you. You don't need to know the details, you just ask for what you want by a general type. The builder pattern is useful when you need to construct a complex object with many optional parts. Instead of having a messy constructor with a dozen parameters, the builder pattern lets you create the object step by step with a fluent, readable interface, like new car builder, with color, red. With engine, V8. Build. When your application needs to talk to a database, writing all the code to connect, query, and map results to Java objects can be tedious and error-prone. This is where an object relational mapping framework like Hibernate comes in. Hibernate acts as a bridge between your Java objects and the relational database tables. You work with your familiar Java objects, and Hibernate automatically handles the messy SQL code to save, update, delete, and retrieve them from the database. It uses a session factory to create session objects. The session is a short-lived object that you use to perform database operations like session.save, myObject, or session.get, myClass.class, Core annotations like @entity mark a class as a database table, and @id marks a field as the primary key. Finally, as applications grow even larger, managing all the different components and their dependencies becomes a huge challenge. The Spring Framework is a massive and popular framework whose main goal is to make developing enterprise-level Java applications easier. At its core, it manages the lifecycle of your objects and wires them together using a principle called dependency injection. You simply declare what components a class needs, and Spring provides them automatically. The Spring Boot project makes it incredibly easy to create standalone production-grade Spring applications with minimal configuration. An annotation like its Spring Boot application turns a simple class into a fully functional web application server. Other common annotations like @REST-controller define a class that handles web requests, @AutoWired automatically injects dependencies, and @Service marks a class for business logic. These frameworks provide the powerful scaffolding needed to build the amazing, complex software that powers our world.